Today we'll be talking about limit profiles for interacting particle systems. My talk will focus on the interchange process, so card shuffling. And so I'll start by defining what the interchange process is about. So I know the notes are available for everyone to see, but I might diverge here and there. I'll try to follow it closely. So the interchange process goes as follows. So you start with a finite graph in my case, with vertex set V and edge set E. Let's say that the size of the vertex set is N. What you do is that for your process, you pick an edge uniformly at random. It could be a loop as well. And you, oh, wait, before that, you don't pick an edge. You place nodes, you place particles. Place one particle per side. Okay, that's and in the case of per vertex per side. In the case of the interchange process, we have n distinct particles, 1 through n. Okay, and different processes we'll see that that can be different. But for the interchange process, we have n distinct particles. We place a particle per vertex, and what we do is that at each step, we pick a vertex, an edge, uniformly at random. Okay. And we swap the nodes that are at the ends of this edge. Okay, and that's at the ends of the vertex, yes. And that's the process. And one question for today is something of the form, for how long do we need to repeat this till, you get some sort of random configuration. So I will rephrase this type of setup in the case of, in the wording of card shuffling. And the way to do it is to say, okay, what happens, for example, in the interchange process if we look, say, at the complete graph? Okay, so any two nodes are connected. Let's say I also add a loop for each vertex, and the interchange process in this case corresponds to shuffling by random transpositions. So let's consider a deck of n distinct cards. And the way we're gonna shuffle is by random transpositions. So this will be one of the two transpositions. Models, card shuffling models we will talk about today. When we do random transpositions, what we do is that we pick two cards uniformly at random and independently of each other. And we swap them. And I already sort of told you in terms of the interchange process that the question we like to ask, or one question we like to ask, but in terms of card shuffling, perhaps it makes more sense about why we ask this, is, how long do we need to shuffle? How long does it take for us to shuffle the deck well enough? And I'll turn this into math in a minute. So we repeat this process of picking two cards uniformly at random independently and swapping them. And we want to know how long until we shuffle the deck well enough. And, I mean, we will all agree that this is not the best way to shuffle a deck of cards. In fact, it's a famous theorem by Diaconis and Shashahani, and we will talk a little more about this. That it takes 1/2 n log n steps to shuffle the deck in this way. Again, I'll turn everything into math soon. So it takes a long time, especially if you plug in n equals 52, it takes a long time. But up to today, this is one of the best models that approximates in some sense the way that DNA sequences behave. And in terms of math, this was the first card shuffling model where, Diaconis and Shahani introduced the technique of using representation theory and algebra to study card shuffling. So it has a mathematical merit. The other interchange process I will be talking about today is, well, perhaps let's go to a new page. What happens if we consider the star graph? So now there is one node that is connected to everyone else. And then possibly we also add loops at each vertex, a loop per vertex. So in terms of card shuffling, if you do the interchange process on a star graph, we get what is called the star transpositions. And it is really the name is really motivated because of the star graph. So what do we do according to the star transposition shuffle? We pick one card uniformly at random. And we swap it with the top card. Okay, and if we want to ask again how long it takes to shuffle the deck this way, Diaconis used the work of Flato, Oglisco, and Wales to prove that it takes n log n steps to shuffle the deck. So these are the main two models that I'll be talking about, the random transpositions and the star transpositions. So it's a good moment if you have any questions as far as the models are concerned, you should ask them now, make sure you understand them, because I'll keep referring to these two card shuffles all the time. If not, then I will continue with the mathematical setup. So let's try to make everything rigorous and, talk math now. So first of all, I want to make it clear that when we talk about, card shuffling, and we collect the configurations, possible configurations of the deck, you have n cards, they can be in any order. That's really is the symmetric group. So for example, when we buy a deck of 52 cards, they come in order. And that corresponds to the identity element of the group. Say we want to transpose the top two cards. So let's say number 2 comes first and then 1, and everything else is in order. That really corresponds to the transposition 1, 2, and so on. Really, you can, create the permutation that the deck somehow defines. So that's why we will be, a card shuffling is really a Markov chain on the symmetric group. And so to give our definitions, we will consider two permutations in the symmetric group, and we will build the transition matrix. So the object, that captures almost everything today is a transition matrix. So the XY entry of the transition matrix, so it's an n factorial by n factorial matrix, the XY entry of this matrix really is the probability of moving from X to Y after one step. And okay, so this is a matrix because, we let X vary and we let Y vary in Sn. So this is an n factorial by n factorial matrix. And of course, random transpositions will have a transition matrix. Star transpositions will have a different matrix because, the definition of the transition matrix heavily relies on the, the model. Okay, so now we want to capture, doing the process again and again. So this means that we will be taking powers of the matrix, and the XY entry of P to the T will be giving the probability of moving from X to Y after T steps. Okay. And just the notation, we will be putting the starting point down there, so that this is now the Xth row of the transition matrix, which is a probability measure, meaning that if we add in terms of Y, we will be getting 1. We must land somewhere after T steps. And what happens now is that we want to let time go to infinity. And we notice that this XY entry will look more and more, in these two cases at least. I don't want to talk about assumptions of when this is true, but in these two examples I gave, the XY entry will look more and more like 1 over n factorial as t goes to infinity. So we will be converging to the uniform measure. And we study this convergence, or usually we like to study this convergence with respect to the total variation distance. Let's define the total variation distance. It really is just L1 norm. So bear with me a few more definitions, but I think that they will be useful both for my talk and Dominic's talk. So just a small setup. So the distance between the X row of the transition matrix to the power of T from the uniform distribution, so this is the notation for uniform on Sn, uniform measure on Sn, is just 1/2 their L1 distance. So this is the traditional norm that we like to play with. And even though for these two models, it really doesn't matter where you start from, things are pretty symmetric in the symmetric group and in the way that we define the card shuffles. However, generally for Markov chains, we like to take the worst case starting scenario. And this is when I say, sometimes I will need the starting point and sometimes I will not, but when I say total variation distance, you can assume I mean the worst case one. So to quantify what I meant by, how long does it take for the deck to get shuffled well enough, that's what the mixing times or the mixing time of the card shuffle is. So if you give me an error, so an epsilon that is positive, then hopefully I will be able to tell you what is the first time that this total variation distance becomes less than epsilon. So we will never be equal to the uniform measure. There will be an error, but that's fine. So, and now I'm ready. I can write at least the first theorem that I promised you, which was the Diaconis-Ashahani. So this is their seminal work. Okay. So for random transpositions, first of all, if we take 1/2 n log n steps plus a little bit more, then the total variation distance becomes less than e to the minus c. So over here, I'm lying. There might be some constants I'm throwing under the rug, but very soon I will give you a very precise statement. So It's roughly that. And part B says that if we take a few less steps, then if we take total variation distance at this time, and of course there is a dependence on n and c on t when I write it this way, and I take first the limit in terms of n and then the limit in terms of c, that is going to be 1. So we're really not shuffled well enough. So this is what describes the occurrence of the cutoff phenomenon. So I'll explain what this is in a moment. Let's say the occurrence of cutoff. Okay. If there are any questions on the setup, now is a good, or the theorem of Diaconis-Shashahani, now is a good time to ask, because now we are getting a little bit closer to the subject of the talk, which is limit profiles. I think I see something on the chat. What happens if Cn is replaced by Cn to the alpha? Very good. Alpha is less than 1. Then there is an issue. I don't think, I'll give you the definition of cutoff in a moment. You do need the window to be of order exactly n. Let me write, let me write the next statements about limit profiles. But yeah, so all I'm saying is that this will not be going to 0 as n goes to infinity and c goes to infinity. And the leading eigenvalues will cause trouble. Okay, good. I'm happy you're happy. So yeah, I should be doing this here. Okay. So let's define cutoff, and I think that hopefully things will get a little bit clearer. The window is very important indeed. So the cutoff phenomenon. Now I will define it in general for Markov chains. I'll try at least. So if we have, say, a Markov chain on a finite space omega, let's say with size, let's call it capital N, just not to mix with little n, we say that xt exhibits cutoff at, say, Tn, with a time Tn, with window Wn, if 1, Wn is little o of Tn. I will make the comparison with the theorem we just saw. 2, if we take the total variation distance at time Tn plus a little more, which is determined by the window, so c times the window, and we send first n to infinity and then c to infinity, then this limit is 0. And 3, if we set c to infinity again, n to infinity again, but now we take a few less steps, so we subtract the window terms, then we get 1. So for Diaconis-Shashahani, we had Tn to be 1/2 n log n, and Wn to be, say, 1/2 n. You'll see why I keep the 1/2, why I insist on this. So indeed, the window is of smaller order than the main term, and that's exactly what we wrote in the theorem. So this is what describes cutoff, or at least I'm defining it the way that I need for this talk. Let me just say, now that we saw, before we continue for limit profiles, let me just say that for star transpositions, I don't want to have to write all of this again. I'll just say that, so this was what Diaconis proved, as I said, using the works of flat-out Lisco Wales, that for star transpositions, or actually, let me, as I said, phrase it in terms of cutoff now that we have defined it, star transpositions exhibit cutoff at n log n with window n. And as I say this, I realize that even though I introduced the capital N, I still used the small n. So I want to correct this for a moment. It's not too bad, but as I said, these little n and capital N's are different. And hopefully I fixed it everywhere now, just for the slides to look fine. Okay, so because capital N in the case of the card shuffle is n factorial, so but you know, I'm using notation here, not putting n factorial and just putting the parameter. Okay, so I hope I have not confused you. I hope that the definition of cutoff makes sense and that the examples motivated. So now I want to proceed to limit profiles. Okay, good. For a moment, my iPad got stuck. That was scary. So what I want to say now is for the definition of limit profiles.
Sorry to interrupt you.
Yes.
I'm sorry. I didn't find how to hang forgot the name. Anyway, I wanted to ask you if it is possible that you have, because here you have cutoff with window omega n, but is it possible to have cutoff with window omega n and cutoff with some window omega prime n? I mean, if omega prime n is smaller than omega n.
Right, I see what you're saying. So we do try to how to say it, get the optimal type of window. So what I'm trying to say is if, yes, okay, you're saying that my definition is not properly stated. I stated it the way I wanted to. But for example, if you could prove, say, for random transpositions, that, hey, this is true, the part 2 is true for Wn n log n, for example, but for some reason you cannot control the upper bound very well. And say your lower bound is still order n, so you can prove, then we would still communicate to each other that, hey, the window we have found is the worst one, the n log n, but we expect it, for example, to be the other one. I don't know. I have not seen occurrences I have not seen occurrences where usually we believe that there is one order that makes it work, if I may ask your question, but
yes, it is exactly my question. And maybe the limit profile is specifying exactly if it's time window.
So for the limit profile, I need you know, upper and lower bound to have the same window, and you'll see I'll need it to have the optimal some sense window.
Optimal window. Ah, okay.
Yeah. Let me write down what the definition of limit profile is. I mean, I'm not giving satisfactory answers to you just because I think this is a very delicate area. You'll see in a moment in the limit profile how the definition, I don't know if it is well defined all the time. So bear with me, okay? But very good question. Very good question. Thank you so much. So for the limit profile, what we want to say is, okay, let's take the limit as n goes to infinity of, you know, Tn plus Cwn. So now C is allowed to be negative as well. And if this exists as a function of C, then that's what we call the limit profile. So if this is well defined. So here I want the optimal window. And again, you know, you will get different answers, of course, if, for example, not two different, but different answers if you have this 1/2 or not, you'll see. But somehow I'm saying drop this last limit and see if this function exists. And to this day, I don't know under what conditions this is well defined. This is sort of helping us understand the standard cutoff picture that people draw, which is that, you know, you take total variation distance and you take time and you start at 1 because at the beginning you're really not random, and you really stay not random, and then suddenly it drops. So that's what cutoff, that's the standard picture for cutoff. But for me, you can also say, hey, this is also a limit profile type of question, because it's cool to know the entire picture, not just the limits that, you know, meaning the entire picture is right here, what's happening. So not only what's happening before and what's happening after, but really the shape of, the exact shape of decay. So let me give you, again, now you can complain as much as you want, because I don't know whether this is well defined. Also, you don't need to have cutoff to study such an object. You know, we do know that simple random walk on a cycle converges to Brownian motion, but it does not exhibit cutoff. So you can ask anything you want. But for now, for the cases where we know that this type of thing exists, we will be calling it, you know, the limit profile. And so the first theorem for limit profiles that I want to mention, oh, before I mention this, I want to say that people have been proving limit profile statements for a long time. So going all the way back to the riffle shuffles by Bayer and Diaconis, they do get the limit profile for the way that we should all shuffle a deck of cards, which is to roughly cut the deck into half and riffle. Or we know limit profiles for you know, random walks on Ramanujan graphs. It came from the central limit theorem. So people were able to get limit profiles. And Dominic will tell you many, many more examples from exclusion processes. Okay, not many, but more examples. We don't know that many. What I'm trying to say in this talk is that now we are making an effort to actually create techniques that could be used to study limit profiles and not just go case by case. It's just that these two examples I gave you very naturally give can help us understand, you know, what the limit profile is. So the first theorem is due to Luca Tessier, and he proved that for random transpositions, let's say with at the cutoff time, and the window time to be 1/2 n, the limit profile is a total variation distance. So the total variation distance is 1/2 the L1 norm again. I will use this notation for general measures. So total variation distance between a Poisson 1 and a Poisson 1 plus e to the minus c. So this was a long-standing conjecture of Diaconis, because based on a work of Matthews. So Matthews was looking at the number of fixed points while you perform random transpositions, and that converges to this type of thing, like a Poisson 1. But as you do the process, this is the random variable that you're getting, basically, when you look at fixed points. And so Luca was able to use representation theory to, you know, prove this. The theorem for today, the theorem I will be discussing mostly today is the following, which, yes, which also introduced it. But both these theorems introduced techniques for us to study limit profiles. So for star transpositions, now, let's say the cutoff time Tn bar is n log n, and the window, let's say W bar n being n, the limit profile is the same. The only thing that changes is the cutoff time and the window time. Let's say phi bar C is again, the same thing. I'll explain in a minute why, even though Lucas' setup was already hard enough, in some sense, you have more tools when you are shuffling with all of the transpositions. They define a conjugacy class in the symmetric group, and that's quite powerful. With star transpositions, you kill some nice algebraic behaviors, but at the end, the idea of the technique that I was trying to build up was that, whether you do interchange on the star graph or whether you do interchange on the complete graph, these two things behave roughly the same because if we think of simple random walks for a moment, on the star graph, taking 2 steps, you can land anywhere with almost the correct probability as if you were on the correct graph and you were just taking 1 step. So this is a heuristic. It's not a rigorous statement, but this is what led me to believe that these 2 card shuffles must have the same limit profile. And, it helped me introduce a comparison technique and say, okay, whatever limit profile random transposition has, star transpositions should have the same. Okay, so let's get into the techniques now for the last 10 to 15 minutes. Any questions about the statements of these 2 theorems? You see, for example, that if I drop this 1/2, there will be a 2 appearing here and so on. So, and we do need the correct order of the window to state something like this. Okay, so no questions. So I will continue with techniques once my iPad behaves. Come on. Oh, perhaps it's Zoom. There we go. Okay, so okay, so the way that we will go about is that we will have 2 transition matrices, P and Q. P for the random transpositions, Q for the star transpositions. Okay. But perhaps let's define it, just with the transition matrices of random transpositions and star transpositions. Okay, so what happens now is that we should notice that P and Q are symmetric matrices. What does that mean in terms of the processes? It means that when you make a move, then with equal probability, you can undo the move on the next step, basically. So this is what's happening. And this means that we have the spectral theorem. So they have real eigenvalues. Let's say P0, P1, and then n factorial -1, because we have n factorial 1 of those. Standard graph theory type of arguments give us that because P and Q use generating sets of the symmetric group and the identity is in them. So the identity gets a non-trivial map. You stay fixed with non-trivial probability is what I mean. The largest eigenvalue is 1. The second largest is strictly less than 1. And the smallest eigenvalue is less than -1. So that's true for random transpositions and both for random and star transpositions. So these are, let's say these are the eigenvalues. Just for the notation, these are the eigenvalues of random transpositions. And let's say for notation again, Q0, Q1. The Q1s are the eigenvalues of star transpositions. Okay, so that's the notation. We will also mention the eigenfunctions in a moment. But we will not use them here much. So the standard L2 bound, when you want to just when you want to just study mixing times, then roughly, so this is a oversimplification of Diaconis and Shashahani, but still it's correct. It's not, I'm not lying to you, is that if you take the total variation distance, you square it and you multiply by 4, then this is less or equal to adding the eigenvalues to the 2t, but we exclude the very first one, we exclude the 0 eigenvalue. So remember, the biggest one was 1, that gets excluded. Good. Usually, so this is true for random transpositions and star transpositions. For more general Markov chains, you do need to include also the eigenfunctions over here. There's an extra term, but no need for us to do that. To determine the limit profile, so if I was to write the correct, not the correct, but the exact inequalities that Diaconis and Shashahani used, or the one that Teissier used, I would have to talk about representation theory. So I don't want to do that. I will show you something, in terms of things that we all understand. So to determine the limit profile, what Teissier roughly did, but this is something that appears in a paper of mine with Samuel Taylor, so this version appears there. So if you consider a subset of your eigenvalues, and you want to look at the total variation distance, say you start at the identity, I told you it doesn't matter when you are in the symmetric group, and you add, you subtract, I'm sorry, only a few terms. So here we take only the things that you care for, the main terms, and now the eigenvalue, the eigenvectors appear. I will define everything. I just want you to bear with me. Write it correctly, and then I'll explain it. Okay, let me explain what's happening here. So the total variation distance, there is a formula that says that it is exactly equal to this type of thing, but for all I, not just the special ones. So here, we will only keep the ones that we like, and the rest are going to go to the error. These FIs are just the eigenvectors. Eigenvectors in the symmetric group, and this is the coordinate that corresponds to the identity. So that's the only time we'll see the eigenvectors appear. Look at this. This is a very general formula that works for reversible Markov chains, and that's why I'm saying you can find it and work with Samuel Taylor. But Lucas-Teissier's formula was A, in terms of representation theory, and B, way sharper. Here, if you were to actually do this for random transpositions, you wouldn't be able to get the nice thing that he got. But there are other Markov chains where this formula gives the limit profile. I just wanted to write something that we can understand and roughly tells you what the technique that Luca introduced was about. What I want to go more towards too is the comparison theorem. So let's see. Yes, I have some space. So comparison theorem, and I know that perhaps Dominic might use this, so let's try to state it carefully. So comparison theorem for limit profiles. Okay, so I already hinted that P and Q, meaning the transition matrices for star and random transpositions, behave similarly. How so? What is the similarity that we need? So generally, if we have P, Q, B, two transition matrices, you keep in mind the card shuffles we talked about. Let's say on the same state space omega, that commute. So we want PQ to be equal to QP and have the same stationary measure. So for us, that's the uniform measure. So these are the two assumptions. Let's go with that. Now, if P, just for notation, exhibits cutoff. Oh, here, by the way, sorry, it's important that we're reversible. I shouldn't. So we are symmetric. That's what it means. If P exhibits cutoff at Tn with window Wn, and let's say has eigenvalues, the PI things that we said, and then Q exhibits cutoff at the same things but with bars. Then here is the inequality that gives us the same behavior. So, okay, here I assume that the limit profiles exist, but that's because I do not want to have to write lim subs, lim infs, or whatever. So let's say the two limit profiles exist. Then to bound their distance, all we need to do is look at the eigenvalues of the first one at the cutoff time plus the window, CWN, minus the eigenvalues of the other one. So with bars at the respective cutoff time squared. Here, it doesn't matter. If you include the first one, they're both one, so it will be 0. So I might as well just include it. Okay, yeah, I should have been putting capital N, so I'm not gonna do it now. And then, okay, this inequality, the way I write it right now, is correct for random transpositions and star transpositions, but generally you also need the respective eigenfunction. So if you have a starting point x, you need the eigenvector at x squared. And let me see, I see a question in the chat. What is pi I? Yes, yes, so, sorry, I'm confused about this last question.
Evita, I think it's the pi in the last formula. I think that should be a p, right?
Yes, that's correct. Correct. Thank you. Thank you. Good catch. It's the eigenvalue. Thank you so much for paying attention. So now what happens is that, first of all, I want to discuss for 1 minute. I know I'm almost out of time, but for 1 minute, I want to say that this assumption might seem strong, but it isn't. So whenever we walk on a random walk, whenever we walk on a group with a conjugacy class, so random transpositions, and then we have another random walk on the same group, star transpositions, these two things must commute. So it's a cute little theorem that was pointed out to me by Laurent Solovkos, that whenever you have a conjugacy class, you'll have a commutativity statement with another random walk on the same group. So this might look too strong, but it is not. And then what is strong is that this type of theorem requires that you know the entire spectrum of the two matrices. In these two examples, we do know everything for random transpositions because of the work of Daiko Nishashahani. We know everything for star transpositions because of work of Flatto, Lisko, Wales. And then the hard work is to actually put those things under the cutoff time and show that they're very, very, very close. And so this is basically how we prove that. So this is the technique. I will not say more, but there's no need to go into any representation theory, but this is how we prove that star transpositions and random transpositions have the same limit profile. So limit profile, meaning that we just prove, and I will not do it, we just prove that this limit, again, I see capital N's, little n's, at this point it's, I guess I was writing it in my mind for these two shuffles. So I just want to write that this limit is just 0 in these two shuffles. And this is all we took to prove the same limiting profile behavior. Okay, so thank you very much for your attention. That's all I had to say for today.